Good day. So today we're going to do a preventive maintenance schedule here on a older, about 10, maybe 12-year-old Goodman air conditioner. It's a 3-ton unit. I always like to start by checking all the electrical first. So the first thing I'm going to do is access the electrical and take a look in there. Okay, so I've accessed the electrical. As you can see, we've got the contactor, the step-down transformer, and there's the high limit switch for the furnace right there. There's my evaporator. This one is using an HVACR metering device, and that's a piston type of metering device. And then in the electrical section we have the IFC, the integrated furnace control, which controls all the sequence of operation of the system for heating and cooling mode. And then I've got my run capacitors for the outdoor fan motor and the compressor. So the first thing you want to do is always start by checking to make sure all the electrical connections are good and tight. But to do that, before we do that, we want to be safe, and we're going to de-energize the unit by turning off the unit disconnect. This one's being a little bit stubborn to open. There it goes. Okay, so on this one, it's just a removable quick connect. So we just remove the quick connect, and there's our bus fuses and the connections to complete the high voltage to the unit. So we're going to put that safely there, and now we're safe to work on the unit. It's always a great idea to assure that the unit is de-energized before coming in contact or messing around with any of the electrical connections. You never know what someone might have done in the past. Somebody might have bypassed one of the fuses for the disconnect here. I've seen that before. So basically the point is, never assume the unit's de-energized just because you've turned off the lever or removed the disconnect. So next step we'll do is we'll take a voltmeter and make sure that the power is indeed off. Okay, so I got my meter ready, and I'm going to check to make sure that the power is off to the unit. I've got my meter set to the highest voltage rated, which is 600 volts for this meter. And I'm going to apply my probes to L1 and L2 at the top of the contactor, at the bottom of the contactor. As you can see, here's where our line power comes in right here and feeds into the bottom of the contactor. You can see that in the past this lead coming in, line 2, had burned some. That means it definitely got hot at one point, and that's from back in the past. In the past, did have a contactor go bad on this unit, and it's been replaced since then. So I'm going to put my meter on here to L1 and L2, and I'm reading 0 volts. So I'm safe to handle anything in here. So what you want to do is, now that you know that you're safe, is just check to make sure all electrical connections are tight. I'm just kind of tugging on these quick connect terminals to make sure that they are indeed tight on the high voltage and low voltage side of the system. So just everything's nice and snug so far here on the contactor, here at the transformer, primary and secondary side of the transformer, making sure that it's tight. That's snug. You could do this with a needle nose pliers too, if you feel more comfortable doing that. Sometimes it's necessary, like maybe on the capacitors. It's easier to use a needle nose plier. And here on the board, J plug is tight. High voltage lead to the furnace is tight. All my connections down here. Everything seems okay so far. So yeah, the other thing you would do while you're here and the power's off is you'd go ahead and clean the logic box out and get all the dust and dirt out of here. And the best way to do that is use some compressed gas, some nitrogen, or if you have a compressed air tank, you could use that. So I still need to check the capacitors. Just kind of giving them a tug. It's awkward to hold this camera and do it at the same time. So yeah, all the connections seem very nice and tight. And as long as I got those capacitors out, I want to test them to make sure that they are still within the correct parameters in microfarads. I have a 35 microfarad run capacitor for the compressor motor and a 5 microfarad capacitor for the outdoor fan. So I'm going to pause for a second and I'm going to disconnect the capacitors one at a time, short them out, and test them with the meter to make sure that they come up to the correct capacitance. Okay, so I've got my meter set up to test capacitance. I got the setting at 200 microfarads. There's not too many capacitors, maybe a start capacitor that's more than 200 microfarads in the HVAC industry. So that's a perfect setting for testing most capacitors for residential, light commercial air conditioning, some small commercial refrigeration. This is the field piece LT17A, so on this particular meter you have to move your red probe from voltage ohm connection over to a special connection for capacitance. You notice the terminal is marked MFD for microfarads. And so I'm going to test this capacitor. I'm starting with the outdoor fan capacitor first, but before testing it I want to short it out and discharge it. By the book, you're supposed to use a 20,000 ohm resistor. I don't know of anybody who does that. I've never done that. Most everybody just uses a screwdriver to short across the terminals. All you want to do is just make sure that the screwdriver goes across both terminals, and that's discharged. The capacitor's discharged now. So any current that was still stored in it is gone. Notice also that I already disconnected one side, one lead from the capacitor first. You cannot get a truly accurate reading of a capacitor while it's still part of the circuit, so you have to disconnect at least one side. And now I'm going to apply the meter and test this run capacitor. Again, kind of awkward holding the phone, and there we go, and the probes at the same time. Okay, so my meter is showing 4.8 microfarads, and we're supposed to be at 5 microfarads, and it's plus or minus 6%. So I would say that we're well within tolerance, and actually these capacitors, both of these capacitors were replaced last spring. They're only a year old, so I already know that both of them are going to test good anyway. I will go ahead and test the compressor run capacitor as well, but we already see how to do that, so I'm going to pause here. So everything checked out good here in the electrical box. Everything was nice and tight. The only thing I haven't done yet is make sure the lugs on the contactor themselves are tight. So I'm just going to really bear down on those screws. They're all nice and tight still. Always check them every year on any unit. Just make sure they're good and tight. Everything else was nice and tight. They do work loose over time, so you will come across units that haven't been serviced in a long time, and you'll find that you can actually torque those down some get them to twist because they're loose. Okay, so over here in the heating section is the only other part I didn't test yet. You know, just kind of check and make sure that all connections are tight for there as long as I'm doing this. And these all look good. These are going to the condenser fan motor and to the compressor. That's the next thing I like to check after I'm done with the electrical compartment, is check the condition of the fan motor. We know that the capacitor is good. It's an older motor. As you can see, it's already developed some rust on the body, and we can't even barely read the data plate anymore on it. And let's see, we're going to take it out anyway and check out the bearings. So the next thing I'm going to do is I'm going to remove all these screws, and I'm going to turn it over so we can access the shaft of the motor to check the integrity of the bearings. I've got the condenser fan motor facing up now so we can access it to check the bearings. So what you want to do is just kind of give it a good spin and see that it spins freely. And we can see that it does do that. And then tug on the motor itself, the shaft I should say, and see if you get any movement up and down, vertical motion. If you do get some motion, that's indicating the bearings are starting to give up. You should not be able to move it any more than maybe a millimeter or two up or down. You feel just a slight movement, if anything at all. Not much at all, really. So it's nice and tight, and it spins freely. It's a little bit rusty, and you can see the rust build up on the shaft. So if we did have to replace this motor, we'd have to use emery cloth to clean that rust off of that shaft, and then also the bottom of it, and use probably a gear puller to get it off and replace the motor. But seems to be fine. Getting ready to mount the condenser fan motor, but afterthought is another thing we should have checked for was to see if the motor needs lubricating. Older condenser fan motors, and even some older machines with on the evaporator fan motor, their bearings need to be lubricated. So what you're looking is for the oil ports that you would use zoom spout oiler to oil the motor with, and there aren't any. So what this is a permanently lubricated bearing, so there's no need to add lubrication. But if you did, this is what you would use. You would use zoom spout oiler. This is what I've always used. It's always recommended, and it's good for motor bearings and regular bearings. The difference between this oil and say 3-in-1 or any other basic lubricant that you could buy at a hardware store is that this oil is non-conducting. It will not conduct electricity, and it is the correct viscosity for electric motor bearings. So that's what you want to use to lubricate any motors. And the only one I have left to check now is the indoor fan, and I'm going to open up the panel to access the indoor blower. I believe it's an ECM, electronically commutated motor, and so there won't be any capacitors to check. We'll just check the electrical connections and check the bearings to see if the motor's turning freely. Okay, so here's the indoor blower. I was wrong. It is a PSC, 2-speed PSC indoor blower motor, and we're looking to see, are there any lubricating ports for this one? And there aren't any. So all we want to do is just kind of, again, same thing. I'm pulling up on the shaft and kind of pulling up and pushing down to see if there's any lateral movement, and then checking to see that it spins freely. that's it. And then we're just going to check the electrical connections, and I will test the capacitor while I'm here. I'll do the same thing that I did on the other motors. Everything's looking tight so far. So I'll pause here and, okay, that's good. And test the capacitor, make sure we're good there. And here's where a thermostat wiring comes into the unit and then travels over to the other side of the machine, to the control board. Houston, we have a problem. So I was testing this run capacitor for the indoor blower, and as soon as I got a closer look at it, you could see that it's been bleeding oil. And when I tested it, and I'll test it for you right now, this is a, oh, by the way, this is a 10 microfarad capacitor. And I'll show you, but when I tested it a minute ago, notice I do have one lead disconnected so that we get a proper test. But I'm only getting 2.6 microfarads out of this thing. And it has been running, but still, that's no good. This would definitely lead to an issue later, probably right about when it's a 100-degree day. It probably give up on us. And this is, again, awkward to do with holding the phone at the same time. It's like working with chopsticks. Okay, so there you go. 10 microfarad capacitor, only coming up to 2.6 microfarads. So this is definitely a bad capacitor. You're seeing the real deal. Okay, so gotta get the capacitor. Unit on the same roof. This is a 4-ton Goodman, and you can see it's pretty much the same. It's just larger. I don't know if you can tell about that by the video, but it's exactly the same, but it's definitely a little bit taller. It's got a bigger evaporator, and other than that, it's exactly the same thing we saw over there. They got an inducer fan motor relay, I think, there, or is that the indoor fan relay? Anyway, so I was going to check the capacitance on this dual capacitor. I know some students get confused about dual capacitors. It's basically two capacitors in one body. So this is still the original capacitor, so I thought I might see something interesting on this one this year. This is still the original capacitor for this machine. This machine's a little bit newer. I think this one's about 8 years old now. So we'll see what happens when I test this dual capacitor. It's two capacitors in one body, and you'll notice that one connection is labeled fan. So that goes to the outdoor fan. The other connection is labeled HERM for hermetic compressor. So that's the capacitor for the compressor, and this terminal is labeled C for common, and that lead goes back to the contactor, and it's getting line voltage from the contactor. So that connection C is common to the two capacitors inside this body, and it is a 55 microfarad for the compressor and a 5 microfarad for the outdoor fan motor. So I'm going to test both of these, and we'll see what we come up with. Make sure that they're still good. I'll be testing a dual capacitor. Dual capacitors, two capacitors in one body. This one is a 55 microfarad and a 5 microfarad. So I wanted to show you guys how to test a dual capacitor. So I disconnected the connection to the outdoor fan. That's what this capacitor is for. It's two capacitors. One's for the compressors, one's for the outdoor fan. I've disconnected the outdoor fan motor and the compressor. And the only connection that's still there is the common lead coming from the contactor to feed power to the capacitor. And everything is de-energized and turned off already. So I'm testing from common to HERM, and I'm getting 54.8 microfarads, so that's okay. and then going from common to fan. If I can get on there. It's like working with chopsticks here. I'm so uncoordinated. Okay, so, and I'm getting 5 microfarads from common to fan. So this dual capacitor is in good shape. We're looking good. And I've already checked the electrical on this. This is a second unit on the same roof. This is a 4-ton Goodman. Brand new run capacitor for our indoor blower motor. And I'm going to check it out real quick. This is a Titan HD. Made in the USA, baby. Yeah, okay, so I just want to make sure it's good. It's supposed to be 10 microfarads plus or minus 5%. So, still got my meter set up for capacitance. It's turning it to 200 microfarads. Trying to do the chopstick thing here again. There we go. Okay, I got 9.9 microfarads. So I'm going to go ahead and put this new capacitor in. As you can see, the old one is still there, so I could easily just transfer the connections over to the new capacitor easily. So purple and I guess it's kind of supposed to be red or pink goes on one side and brown on the other. So just gonna move those connections on over and mount it up. I'll do that now. It'd be easier with 2 hands. Okay, whoops. Sorry about that. So I got it mounted again. Brand new capacitor in place. Boot. All the connections are nice and tight. So pretty much done over here. The fan is moving freely. As you can see, the wind is moving it. You can see the armature inside moving, fan moving. That's just from the breeze. On the indoor blower motor for the second unit up here. This is the 4-ton unit that I'm working on now. Just checking out the indoor blower, and this does have an ECM, electronically commutated motor. So the only thing to do here was check and make sure the electrical connections were tight, and everything looks good here. It's fairly clean. A little could use some cleanup, and so all you could do is just check to see if the bearings are good. I'm pulling up and down on the fan right now. There's no play on the shaft, and it does spin freely. Not quite as freely as a PSC. As you notice, it's already slowing down and stopping, and that's normal for an ECM not to spin quite as freely as a PSC, because it has a permanently magnetized rotor, so that magnet's gonna drag it down and make it, you can see it rocking back and forth. That's from the magnet. It's going to make it slow down sooner because of the magnetism, and that's normal. So everything's good here on this one. The next step is got all my electrical and everything reassembled again. Got everything checked out, the fan motors, the electrical connections, the electrical boxes are cleaned out. The units are cleaned as much as possible except for the condenser coil. And what I wanted to go over is some ladder safety here with you. I am using a ladder that's a little too short for one thing. But the main thing I wanted to show you is that the hose, the position of my hose is well away from my ladder, so that as I pull my hose up, I don't pull my ladder over. So that's really important. Little safety tip for you. So when you clean the condenser coil, let's see what kind of stream I got here. Oh, I need a solid stream. So I'm adjusting it to where it's a fairly solid stream of water. And what you want to do is work your way from top to bottom, going from side to side, so that the stream of water is always directly head on, even straight on with the fins of the coil. Because if you have a lot of water pressure wherever you're at, you could accidentally, inadvertently bend over the fins of the coil, and that restricts airflow, so you don't want that. So here's how it's done. Start at the top, work your way across, and just work your way down, kind of in a serpentine order. And we're starting to see the water come out the bottom there. And here's how you can know when you got it clean, is when you start to see clean water coming out of the machine as it drains out. So again, I'm just working my way back and forth evenly, side to side, trying to keep the stream of water straight on. The coil actually bends around in this corner to the front, the other side. So I try to angle it a little bit right here in this corner. Other than that, just keep going straight across, side to side, working your way down. As you can see, the water coming out is still fairly dirty. There's a lot of dirt accumulated in the coil and then inside the machine in there where the compressor is at. So you can see now that I'm getting to the bottom, the water's starting to clear up. So this part of it's pretty clean. So now I go to the other side here and work this part. This is the bigger surface area here. There we go. So here's where the coil bends. So I want to come in at a little bit of an angle over here. I'm just going to work this corner with the water at a slight angle in this corner so I'm straight on with the fins. And I'm not hitting it too hard with the pressure. I'm kind of got it throttled down a little bit. Okay, so now I'm at the flat part, so now I'll do the same thing. Start at the top and go evenly across, side to side, working your way down. Nice and even. This coil's not that dirty because, well, I'm always pretty good about cleaning it every year. I do care about my energy bill, and this very simple task right here can definitely save you energy dollars over the years, because if you got a nice clean condenser coil, then your high side pressures won't be as high as it would with a dirty coil, and so your compressor motor doesn't draw as much current, and over time that definitely saves you money and possibly expensive repair bills down the road. If the condenser coil gets too darn dirty, then your head pressures go so high that it eventually becomes damaging to the compressor. It'll start out by just short cycling on an overload, and then the troubles just get worse from there. The motor's working so hard, it just reduces the longevity of the motor. So that's about it. You just keep working it side to side, working your way down. Now, this is just regular dirty coil, just regular dirt. If you had a condenser coil that was filthy dirty from grease and dirt, like at a restaurant, then you'd have to use chemicals. But you always want to avoid using chemicals unless you absolutely must. If it's just dirt, then just what we're doing here right now is all that's needed. Now if you come across one that's really dirty, or it's a 5-ton high efficiency unit, it's probably got a split condenser. It's a coil behind the coil. So you might have to remove the condenser fan motor and wash from the inside as well as the outside to be able to get a really good thorough clean. As you can see, the water coming out of the bottom here is nice and clean now. It's not dirty anymore at all. So yeah, it's I think the majority of the dirt was just accumulated at the bottom of the pan there. The coil itself was actually already fairly clean, but no worries, we definitely got it clean now. That's the final step of doing this preventive maintenance on this Goodman 3-ton unit. The last thing I'm going to do is check the evaporator split, and to do that I need to check the temperature of the air entering and leaving the evaporator. So what I want to do is test the temperature difference of the return air and supply air. So to do that, the best way on most units is just to go right into the plenum. This one's never been done before, so we need to drill a hole to put in our temperature sensor. And the best place to do it is right about center of the plenum, and always on the side, never ever on the top, because you have to consider rain. And yes, we're still going to plug the hole, but just don't want any worries about water getting inside and running down the ductwork and into the house. So we always go into the side of the plenum. I'm going to drill a hole right about there. Whoop. Trying to do this one-handed is interesting. Okay, so one of our sensors, T1, I think this is going to be supply. So actually, I'm going to make this T2. Supply will be T2, and return air, which will be the warm air coming from the house, will be T1. So then you just got to insert your sensor into the ductwork. You have to get it not only past the hole, but past the insulation on the inside of the ductwork. There's a layer of insulation just inside that wall. So I'm trying to straighten out my probe so it'll go in there directly, hopefully. I want to feel it go into the stream, into the center of the ductwork if I can. I think it's, no, I got to get past the insulation, so I got to drill again, I think. Something in there keeping the probe from going all the way in. I think it's insulation just inside the plenum there. There, it's better. I can feel it sliding right on in there. Okay, so we want to get it in there deep enough where it's definitely in the airstream. So we'll do that same thing on the other side. So there's temperature 1. It's 93 degrees inside that ductwork. It's about 83 degrees outside here up on the roof. 84 maybe. So after we're done with this test, we'll use either sheet metal screws or silver tape to plug these holes when we're done. Making sure it's clear there for my probe to go in nice and smooth. So this will be T1. You can see there's two connections there. There's T1 and T2 for temperature 1, temperature 2. And you want to do it that way because it makes life easier when we actually do the measurement. Oh, it's hanging up on something. First time you do this, when you drill a new hole, it's always a little bit, there it goes, I can feel it sliding in easily now. Yeah, no resistance. Going right into the center of the ductwork there. Okay, so it's showing like 110 in there on that one. So that's temperature 1, 110 there, almost 111. T2. Wow, it's really hot. Okay, so for the test, we need the machine running. We're just seeing the temperature of the ductwork inside there right now. So I'm going to pause, because what I got to do next is I'm going to bypass the thermostat and wire. I'm going to undo the thermostat wire here. I'm going to take red, which is coming from our transformer and feeding power to our thermostat. I'm going to undo that. Right now the unit disconnect is still out, so there is no power to the unit right now. And I forgot my jumper wire, so what I'm going to end up doing is I'm just going to wire nut red directly to yellow and green, and that will cause the unit to come on in the cooling mode once I put in the unit disconnect. So I'm going to pause here. Okay, so the unit is running now. Everything's running normally. Compressor, condenser fan. Pretty sure my VAP fan is running fine. Just going to, yeah, it feels like a vibration's coming from there. Okay, so the unit has only been on for about a minute now. And right now, let's see, that's supply, I believe. This is, okay, now that's return. So I got it backwards. So I need to move my probes. So the right side is supply air, and the left is return air. So we can see we've got 50-degree air coming out and 81-degree air entering at this time, but the unit has only been running for less than 2 minutes right now. And so be aware that the machine any refrigeration system has to be running for a minimum of 15 minutes before it gets up to full capacity. So we'll have to wait a few minutes. I'm going to pause and go off into the shade for a few minutes and hang out, and we'll come back and see how it's doing. But in the meantime, I'm going to reverse these probes so that when I hit T1 minus T2, it'll give us the correct number, but it'll be a negative number. Oh, okay, no, it's fine. So right now I got it about a 29-degree difference. So that's not good. But again, the machine's only been on for a few minutes, so we'll pause here and wait and see what it does. Okay, so the unit's been running for about 15, almost 20 minutes now. I've got a 25.2 degree evap split. I'm supposed to be around 18 to 22, so it's a little bit high. That means that the refrigeration system is working fine, but I may have a slight airflow restriction somewhere. The air filter is good, so that's not the problem. So it's just something to do with the ductwork, registers, something. Maybe I'll take a look at that and kind of fool around and see what I can find. But I'm not too worried about a 3-degree out too much. For one thing, this is a rental property, so I don't get to make the choices on what is done with the ductwork. So looking at our compressor amp draw, need to turn the meter back on. So the amp draw looks a little bit low. I'm only pulling about 8.5 amps, and I should be closer to 15 amps. But then again, it's only an 80-degree day today, so it's not like a 95-degree day, 100-degree day. So it's not really running under a full load. But still, that does concern me. I do wonder if it is perhaps a little low on refrigerant. The next step will be to do a complete diagnostics using the Pulsar iConnect iManifold equipment, and we'll see what it has to say about it. Should be interesting. So that's it in regards to doing just a preventive maintenance on a air conditioning or refrigeration system. Those are the basic steps. The last step here now is just to undo my jumper, put the thermostat wiring back the way it's supposed to be, put the panel back in place, and that's it. Last little note on this preventive maintenance check on these units is the air filters. I did replace the air filters. As you can see, there are 3. This first one right here was in the 3-ton unit, which was the subject of most of this video. It was in there for about 45, maybe 50 days. And you can see it's fairly dirty, but it's not clogged. Because one way you could tell is you could check to see if you could see sunlight through it. So that gives you a little bit better perspective. I've seen them where you can't even see light through them. But yeah, it's fairly dirty. It was time. The other 2 came from the 4-ton unit. And the odd thing about the 4-ton unit, and I can't explain why, but it does have a double return. And these filters were in about the same amount of time. As you can see, they were pretty much equal in filth, if you will. So anyway, yeah, that gives you maybe an idea of how quickly the filters do get dirty. And this is in the city of, within the city of Bakersfield. The dust can be pretty bad in Bakersfield, but it's not as bad as in the rural areas where there's farming and everything going on. So that's about it. Hope you've learned a lot.